Good evening, everyone. Today I will be discussing about the FTIR signal or spectrum analysis. Okay. So in our last two classes on the FTIR spectroscopy, we have discussed about the basis of FTIR, how do we get this FTIR spectrum and all these things. Then we have also discussed about the instrumentation part. Now, one of the major tricky portion is the analysis of the FTIR spectrum. So we will be discussing this over here. Okay. So as we all know that this FTIR spectrum, it is basically it is an absorption spectroscopy, right? In absorption spectroscopy, we have seen that the results, they are usually they are usually represented either in the absorbance form or in percent transmittance form. Okay. So this is the variable which changes with the change in the chemical component. Now, what is the what is this independent variable over here? The independent variable is the wavelength of the IR radiation. However, in FTIR spectroscopy, we directly do not use wavelength, the term wavelength over here, as in the UV visible spectroscopy, where we use absorption or transmission versus the wavelength. However, in FTIR, we do not use this. In FTIR, what do we use? We use wave number of the IR radiation. While discussing about the wave number, we have also discussed that this energy, it is equal to h mu, which is the frequency, and this can be given by hc by lambda, which is again equals to hc wave number. Okay, so if you see over here, as the energy content is increased, the wave number will also increase. Okay, so higher the energy, we'll be having higher the wave number and we'll be having higher the frequencies. Both wave number and frequencies, they provide us same information. Okay, because what is the relationship between the wave number and the frequency? It is nothing but your mu equals to c multiplied by wave number. So it is a constant there is a constant multiplier c, which is the speed of light. Okay, now as I told you that the x-axis of the FTIR spectroscopy would be containing the wave number, and wave number we have just seen that it is equal to 1 by lambda. So lambda is in it may be in meters, it may be in centimeter, and so on. So herein we have wave number in centimeter inverse. Okay, now what is the y-axis? Y-axis, as I just told you, that it may be either in the absorption or percent transmittance form. So here in FTIR, we usually plot percent transmission. So percent transmission, it starts from 0 and it can go up to 100. Suppose over here we have a peak position of 80%. So this peak is having the maximum dent at 80%. That means 80% of the IR light has transmitted. In other words, we can also say that 20% of the light has been absorbed. Now we know what is there in the x-axis and what is there in the y-axis. Okay. Yeah, another important thing we have also discussed, say that we get this wave numbers directly from the region of say around 400 centimeter inverse to say around 4000 centimeter inverse, 400 or 500 centimeter inverse to 4000 centimeter inverse. So in this case, if you see, if we started with 1000, we have 1500, 2000, and here we may have 3000. Say for example, we have discussed that lower than 1500 centimeter inverse, we are having fingerprint region. And we have also discussed that in this fingerprint region, whatever the peak we will be getting, that peak will mostly be compound specific. Okay. So while we are doing the analysis, we need to understand that we will be working in the region of the wave number which is greater than 1500. Sorry, I am not able to draw the line straight. Okay. So this portion, it is the fingerprint region. Whereas this region, it is the absorption region or functional group region, or we also call not the absorption region, diagnostic region. Or functional group. Why it is called the diagnostic region or the functional group region? As the name suggests, the functional group region, most of the peaks associated with a particular functional group will be present in this region. Okay. Now we have already discussed about the wavelength, frequency and the energy relationship. Then comes the shape of the signal. Now if you see the shape of the signal, if you look into this one, it is a broad signal. Okay. Whereas if you look into this signal component, it is a sharp signal. Okay. Broad signal and sharp signal. So shape of the signal, it may be categorized or divided into a broad signal or a sharp signal. So any broad signal, if you see, it is basically a U-shaped signal, whereas any sharp signal, you will find it is a there will be a V-shaped peak. Okay. So if you are having a U-shaped peak, then it is a broad signal. If it is a V-shaped peak, then it is a sharp signal. Okay. Then intensity wise, intensity means the intensity of the peaks, they can be categorized into three types: weak, medium and strong. Weak, medium and strong. Okay. So weak signals, if you see over here, this signal, it is having a very small intensity. So this is a weak signal. Okay. Whereas this peak, it is a strong signal. Okay. And this peak over here, it is a medium signal. Okay. So in this way, you have to find out. Hearing also, if you see, it is a strong signal. Okay. It is a strong signal. So overall, if we consider this peak, it is a broad come strong signal. Okay. So when you say it is a broad come strong signal, that means it is having a shape which is broad in nature and the intensity of this signal is very high. Okay. Similarly, here also, hearing in this case, the dual peak at around this 3000, it is basically a sharp and strong signal, because if you see the peaks, they are almost V-shaped. Okay. This peak over here at around, say, this is 2500. So you can consider this as around 2300. This peak, it is a sharp and weak signal. It is having a sharp shape, but its intensity is low. If you look over here at this signal component, if you see it is a U-shaped, so it would be a broad and strong signal. Likewise. Okay. So in this way, we categorize this kind of signals. Okay. Now the next thing is that why we obtain these peaks. Some of the peaks, if you see, they are broad signals, and some of the peaks, they are sharp signals. Okay. So why this happens? This is because broad signals, they are mainly exhibited by the polar groups. If you see, most of the polar groups, for example, OH, NH, they can form hydrogen bonding. They can form hydrogen bonding. So these signals OH, NH, they will usually give you a broad signal. Okay. If you look into this CO, if you look over here, so what happens? This is delta positive and this is delta negative. Again, this is delta negative, this is delta positive. So there will be an electrostatic interaction between these CO groups. Okay. So this CO group, since it is having a dipole moment, which is mainly exhibited by many of the hydrophilic compounds. So this group, CO group, it is usually a polar group, and since there is an existence of dipole, which results in a weak interaction within these functional groups, they show a broad peak. Okay. Then we have these sharp signals. So when we have these sharp signals, what are these sharp signals? C double bond C, it is a sharp signal. C triple bond C, it would be a sharp signals, and they are basically non-polar bonds, okay, or non-polar functional groups, okay. So whenever you will be seeing that there is a broad signal, the first thing which will come to your mind that this peak is due to a polar group, whereas when you see a sharp signal, you can say that this group is due to the non-polar groups, okay. Now in general, when you increase the mass of a functional group, the wave number decreases, okay. Now in this case, we have this, see, carbon is, we have kept it as same. However, we have varied the second atom such that the mass increases as we go down. So the CH stretching, if you see, it comes out to be at 3000. When if we replace this H with D, which is having a higher mass, then the stretching comes at 2100. Again, when we replace it with C, so this CC stretching, it will be having at the region of 1000 to 1200. Again, when we replace C with chlorine, it will come down to 600 to 800 centimeter inverse. When we replace chlorine with bromine, it comes down to 550. And when we further increase the mass by including iodine from the bromine, by replacing bromine, we get to the 500. Now see, all of them, they are having the single bond. However, as we are increasing the mass, the stretching vibration, it is coming down significantly. See, from around 3000, it has come down to 500. So there is a drastic movement, 3000 to 500 centimeter inverse. Are you getting my point? Now the next thing is, when the bond strength increases, the wave number also increases. Okay, why this is so? When the bond strength is increasing, that means if you want to initiate the vibration over here, what you have to do? You have to supply more of energy. And we have seen if energy increases, your wave number will also increase. So this fits in our logic. So let us see, C single bond C, it is having a stretching at 1000 to 1200 centimeter inverse. C double bond C, you will be having at 1600 to 1660 centimeter inverse. C triple bond C, we will be having the stretching at 2100 and to 2200 centimeter inverse. Okay. However, if you compare this with this one, okay, so we have Cn, so 1000 to 1200 double bond, if you see 1650 over here also it is around the same region. Again, the C triple bond C, we are having 2100 to 2200. So if you look over here, single bond stretchings, they are at the similar levels, okay, whether it is carbon or whether it is the nitrogen. In these cases, carbon and nitrogen, they will be showing stretching, CC stretching or CN stretching, depending upon what kind of hybridization is there, we will be getting the same thing. Okay. Now, if you see the C-O stretching, it is at 1000 to 1300 centimeter inverse. Okay, if you compare CC and CO, they are at the similar wave number. Okay, they are at the similar wave number, and then we have this C double bond O, which comes out to be at 1700 centimeter inverse. Okay. Now, one interesting thing is that if you look into this, say, if you look into the spectra, FTIR spectra, Suppose here we start with 1500 centimeter inverse and we have drawn a line like this. Okay. Now what is happening? As soon as you are coming from 1500 and you are going towards the 4000 centimeter inverse, just after you get over here, just after you initiate, there will be a peak at around 1600 to 1660. Okay. Now this CC bond, we have seen that they are apolar bonds. So we will be having a sharp peak over here. Okay. Now after this one, so just as you start from 1500 and within the region of 1600 to 1660, if you get a sharp peak, by closing your eyes, you can say there is a C double bond C bond over there. Okay. Then as you move slightly forward, you get C double bond O at around 1700. So, however, this C double bond O, it is a polar bond. So, you will be getting a peak like this. See, C double bond C, C double bond O. You will be getting a big bond. Okay. You're getting my point. So, again, if you move slightly forward after 1700, you may get C triple bond C. If you see C triple bond C bond over here at around 2100 to 2200. Okay. So this is a basic thing. So I will discuss the other things as we move forward. So I am telling initially you will be getting C double bond C, then you will be getting C double bond O, then you will be getting C triple bond C. So C double bond O, it will be having the strongest peak, then the next strongest will be C double bond C, and the third strongest would be the C triple bond C. I will be discussing the other things as we move forward. Okay. So please keep this in mind. So C single bond C 1000 to 1200, C single bond O 1000 to 1300, and since it lies in the region of fingerprint region, so we are not discussing it. So this C triple bond C or C double bond C, if you have C triple bond N or you have C double bond N, they will be appearing at the similar positions. So you have to keep this in mind. Okay. Now the next thing is that when you increase the conjugation, there is a decrease in the wave number. There is a decrease in the wave number. Here, let us take the example of C double bond C. So if you see in the cyclohexane, if we include one single bond, then we get this peak at 1650 cyclohexene. Okay. Then if we include two double bonds, if you see the wave number, it reduces to 1620, and then when we make it more conjugated by including another bond and we convert it into the benzene, the C double bond C stretching, it comes out to be at 1600. So if you see over here, when we talk about C double bond C, if you are having at 1600, towards the 1600, you will find that it will be more conjugated as compared to the C double bond C peaks, which are at the higher wave numbers. Okay. Now some other groups which are sp hybridized, they include, see, SCN AC triple bond N, it is at 2150. Then NCO isocyanate, it is 2250. C double bond C, it is at 1950. And again, if you see C triple bond C, 2100 to 2200 centimeter inverse, and C triple bond N, 2100 to 2200. So if you see, all these sp hybridized carbon atoms, they show peak at around say 2100 to around 2200, with some exceptions. This alien, it is at 1950, and this isocyanate, it is around 2250. So whenever I am telling about this 2100, 2200, you have to keep in mind. So if I can say XXAA, so this A may vary from 20 to 40 wave numbers up and down. So it happens because depending upon your chemical environment, in what solvent you have developed these things, so it varies. This much it varies. Okay, so you have to use your judgment while you are trying to analyze the FTIR peak. Okay, so these are the some of the generalized wave numbers which have been given to you. So the main thing is, the takeaway from this slide is that if you see, we are having 1500. At 1500 we will be having, if it start, so as soon as we move towards the right, we will first be getting C double bond C or C double bond N, then there will be a C double bond O peak, and then there will be C triple bond C peak. Okay, if they are available. Now coming to the alkanes, in the alkanes we have this CH stretching at 2900. At 2900 we get a sharp peak, and we will be getting a peak like this. So if you see, it is just looking just like a mouth. Over here it is looking like a mouth. So CH stretching at 2900, it will be showing you this kind of peak. Okay, so that means if we look over here, so suppose if we draw another line and say 3000, we will be getting a peak something like this for CH stretching. Okay, so this is sp3 hybridized carbon. Okay, this is an sp3 hybridized carbon. Okay, now CH bend for methylene group, it will be coming at around 1400 to 1450, and CH bend for methylene group, it would be coming to 1350 to 1400 centimeter inverse. Okay, but however, since they are in the fingerprint region, we are not discussing it much. Now coming to the alkenes, over here, as we know that alkenes, they will be having a double bond. Now this double bond may be an internal double bond, or it may be an external double bond. Let's say we are having the first chemical like this. The second one is see, I have not given any values over here. Let another thing what I can do is that same. I put it as X. In this way. So herein, this double bond, it is the internal alkene, and due to the presence over here, which is at the terminal position, it is an external alkane. Okay, so C double bond C stretching, it would be appearing at 1660, 1600 to 1660 in both the cases. Okay, however, the CH stretching, in the first case, if your X is equal to H, then what will happen? If your X is equal to H, then you will be getting this CH stretching peak at 3000 to 3100. However, if your X is equal to another functional group, say R, then this CH stretching will not be present over here. Okay, this double bond CH stretching. Okay, double bond CH stretching. So basically, the CH stretching associated with the sp2 hybridized carbon atom. Okay, and in the terminal group, it will be must have. Okay, so once you have analyzed that this group is there, 1600 to 1660, you are getting a peak, so you can confidently say, yeah, C double bond C stretching is there. Then double bond CH stretching, if you see this peak, then you can say that there is a probability that this CH stretching is due to the external stretching, external alkenes. However, the internal alkenes, we need to find out whether this CH stretching is an internal alkene or not. This you have to keep this in mind. So if you look over here, this position 3000 to 3100. So what you will get over here? This is an sp2 hybridized carbon based CH stretching. So if you go back over here, just after we cross 3000, we will get a sharp peak for the sp2 CH stretching. So if you see, just below the 3000 wave number, we'll be getting the sp3 CH stretching. Just above this 3000, we'll be getting a peak of sp2 CH stretching. Now see the nature of the curve. It is only a V-shaped curve. Whereas in the CH stretching, there was a mouth-shaped structure. Okay. Now coming to the alkynes, again in the alkynes, it may be an internal, it may be an external thing. And if you see C triple bond C stretching, we have already discussed, it would be around 2100 to 2200 centimeter inverse. Whereas in the case of triple bond CH stretching, that means sp hybridized CH stretching, for the internal alkynes, you will not get any signal. You will not get any signal. However, for the external alkynes, you will definitely be getting a signal. So why this is so? Let us see. CH3, C triple bond C, CH2, CH3. So this is an internal alkyne. There is no CH bond over here. Okay. Whereas in the second case, CH3, CH2, CH2, C triple bonds C H. So there is one hydrogen. So you will be getting one peak at 3100 to 3300. Now again, let's go back to this peak. It is slightly higher than this sp2ch. You will be getting peak something like this, which will be stronger than the previous one. Okay. Sorry, it's intensity will be similar to this one. So this peak is for the sp hybridized CH stretching. Now coming to the alkynes again, we have discussed about this thing, this alkyne C triple bond C stretching and triple bond CH stretching, and we have discussed this. Now coming to the alkynes, alkynes may be either symmetric or asymmetric. What do you mean by symmetric? Symmetric means C triple bond C, CH3, CH3. Now if you see, if there would be a if you draw a line in the middle, you will see this functional group and this functional group, they are symmetric. Now since they are symmetric, when they will be stretching, the net dipole moment will be 0. So the net dipole moment, it would be 0. Okay. Whereas in the asymmetric case, what you will be getting, say CH3, C triple bond C, then CH2, CH3. There would be a small change in the dipole. Okay. Now in this case, if you get a signal at around 2100 to 2200, that means at around this peak, this C triple bond C, this 2100 to 2200, if you get a peak, if you get a small peak over here, this suggests that there this C triple bond C stretching is due to the asymmetric C triple bond C stretching. Okay. Then CH stretching, if you see, we have already discussed 3100 to 3300, you will see. So if there is a symmetric C triple bond C stretching, you will not get any signal. However, in the case of asymmetric these alkynes, you will be getting peaks at these two locations. So these two locations, which this one A1 and this SPCH hybridized stretching, you will be getting only and only in the case of asymmetric carbon atoms. Okay. However, this CH stretching, it would definitely be there. Now coming to the carbon monoxide, it is a very typical molecule. So when you have this one, so this is delta plus and this is delta negative. Okay. Now if you have this, you have a dipole moment in this direction. Right. Now if you apply an electric field in this way, sorry, negative. So positive will be repelling this bond, and this negative charge, it will be repelling this bond. Why I have drawn this positive and negative? Because we are using infrared radiations, which are electromagnetic radiations, and they have an electrical field. Okay. So if this happens, you will be getting a decrease in the bond of C triple bond C, carbon monoxide. And if there is a decrease in the signal component, the signal strength will be lower. However, if somehow the orientation is in the other way round, then this carbon atom, it will be pulled towards this negative terminal, and this will be O will be pulled towards this positive terminal, and there will be an increase in the bond length, and this bond length increases, and whenever you get the stretching, so the bond will be stretched basically, and hence the bond length will be increased, and you will be getting a medium qualities, medium intensity signals. So it is along the DM. DM means dipole moment. If the electric field is along the dipole moment, there will be a weak signal. If you are doing it against the dipole moment, if the field is against the dipole moment, then there will be a medium signal. Then coming to the carboxylic acid and alcohol. So in the carboxylic acid, we have say C double bond O OH. Okay. Now with stretching, you will be having a broad peak in 2500 to 3300. Okay. So let's go over here. So to 33 to 2500. 3300 to 2500. Down from here, you will be getting a 2500 like this. Okay. Let me change the color. Possible. Let me use another color. There will be a broad peak like this. So this green peak is due to the carboxylic acid. Carboxylic acid OH stretching. Okay. So that will be then for alcohol 3200 to 3500. 3200 to 3500. It is above the 3000. So you will be getting a broad peak, but it will be something like this. Blue I have used in this region. Let's use this one. Something like this. There would be a broad peak at 3200 to 9. Okay. In many cases, this SPCH bonding and this broad peak due to the OH stretching, it overlaps. Okay. Due to the alcohol. So in both the cases, if you see, there would be an OH stretching. Carboxylic OH stretching will be much broader, whereas alcoholic OH stretching, it will be broad, but it would not be as broad as that of the carboxylic acid OH stretching. Then C double bond O stretching. So if you see, in the case of alcohol, we do not have any C double bond O, so this would not be present. In case of double bond O, we will be having this. This at 1700 we have already discussed. We will be having this stretching. Okay. Then CO stretching, because over here you are having C-O. This stretching is there. So this would be the conformation here. Herein, if you see, the carbon is connected to double bond O, so you will be getting the sp2 hybridized stretching. So you will be having in the region of 1200 to 1300, whereas in this case it is the sp3 hybridized carbon, so you will be having this CO stretching in the region of 1000 to 1150. So once you have detected from this carboxylic acid, if you have a broad peak, from there you can have an understanding, yeah, there might be a carboxylic acid stretching, whereas if in is the alcohol, it will be having somewhat at a higher wave number, you will be having the OH stretching. However, in the case of the CO stretching of the acid, it will be at 1200 to 1300, whereas in the case of alcohol, it would be in the region of 1000 to 1150. Okay. So why this is so? If you see this bond, it will be a stronger bond as compared to the this CO bond of the alcohol. That's why if you see this CO stretching in carboxylic acid, it is at a higher wave number. Then aldehyde and ketone. Okay. and herein we will be having ketone like this. Okay, so CO stretching in both the cases we will be having C double bond O, C double bond O. So at 1700 you will be getting stretching. However, in the case of aldehyde, you will be getting this CH stretching at 2700 and 2800 right of the alkane CH stretch. Okay, whereas in the ketone you will not be getting over here. So what does this mean? If you go back, you see this was the alkane, this CH, this is the sp3 hybridized carbon CH stretching. Just right to this we will be having two peaks at 2800 and at 2800 and 2700. Okay. Then coming to the ester and ether. Ester is ether would be something like this. So C double bond O stretching, it will be present in ester. In ether it will not be present. Now CO stretching, if you see over here, it is a hybridized sp3 hybridized carbon. So there will be a stretching at 1000 to 1150. Over here also CO stretching will be there 1000 to 1150. However, in the case of ester there is another sp2 carbon sorry, yeah, sorry, here this is the sp3 carbon, sorry, this is the sp3 carbon. So this CO bonding, it will be at around 1000 to 1150. Here also you will be getting at 1000 to 1150. You will be getting the peak. Whereas there will be another peak at 1200 to 1300, which is next to this C double bond O. So next to C double bond O, we are having another CO stretching. So we will be getting a peak at around 1200 to 1300. So in this way, we can find out whether a given compound is an ester or an ether. Then coming to the amines and amide, how do we find out? We get it in this fashion: RNH2 and herein RC double bond O NH2. So CO stretching, I think I have done some mistake over here. It would not be here. This is not be C double bond O. Yeah, for the C double bond over here, this would not be present. Herein we will be having C double bond O stretching at 1650 to 1690, and then NH stretching in the primary amines. If you see over here, there will be two amines, two hydrogen NH bonds. So we'll be getting double peaks. Okay, one double peak, one peak would be due to the symmetric stretching, the other would be due to the asymmetric stretching, 3300 and 3400. So it is because of RNH. So it can move in plane together. So there can be symmetric stretching of these NH bonds, or there can be asymmetric stretching of these bonds. Okay, so usually when it is in the same direction, you get it at a lower wave number. So symmetric stretching will be at the lower wave number, whereas the asymmetric stretching will be at a higher wave number. And then we will be having this NH stretching for the secondary amines, you will be getting a single peak, because over there we will be having R, N, R, H. So there is only one NH hydrogen bond. So we'll be getting only single peak at around 1200 to 1300 centimeter inverse. Okay. Yeah, and NH bending for the amines, it will be at around 1580 to 1650. Okay. Then CO stretching, if you see the CO stretching groups, so what happens is that whatever are the possible stuffs which are present over here, I have arranged like acid halides, then anhydride, acid anhydrides, then esters, then we have acids, carboxylic acids, alcohols. Sorry, mm, this is aldehyde, sorry, aldehyde, this is ketones, and this is amides. So if you are having an electron donating group over here, then it will be at a lower wave number, whereas for electron withdrawing group, your wave number will be moving towards the higher wave number. Okay, if you are having electron withdrawing group. Then nitro group, in the nitro group there would be two group, double bond O, and this O negative, this thing. So there will be in double bond O stretching at this one 1550 to 1600, and in O stretching at 1300, 1380. Then in aromatic group we will be getting C double bond C stretching at 1600. We have already discussed. However, for the alkenes it is at 1660. Now how to differentiate between the aromatic ring and the alkene? In C double bond C stretching, as I already told you, you will be having at 1600 and 1660 for the alkene. Whereas apart from this, the aromatic group will also be having peaks at 1475 to 1500 centimeter inverse. And then we will be having this double bond CH stretching, both will be having at this location. So to summarize, what we can discuss, we can discuss like this. If we start with 1500, initially, as soon as we start, we get a C double bond C stretching. Then we have a group called C double bond O stretching. Then if there is an aromatic ring over here, we will be having some overtones. These zigzag like systems will be there. These are called overtones, and these are due to the aromatic ring. Okay, then if we move forward, we can have C triple bond C and C triple bond N. Okay, then we again move forward, we will be getting double teeth. So this is sp3 CH stretching, and after just before 3000, then after that we will be having, sorry, at this location. Then if it is like this, we will get an, sorry, there is an sp2 CH will be there. And then further as we move, we can have SPCH stretching. Then over here we will be having the OH stretching. Okay. However, if there is This is a primary amino group for something like that. If it is a primary amino group, so we can see we have RNH2, so there will be two NH transitions, something like this you will be getting. And if it is a secondary amino group, RNHR dash, then we will be having this is for the secondary amine, and the black one, it is for the primary amine. Okay. Then if we have carboxylic acid, we'll be having a very strong peak. Okay, a strong and broad. We will be having a very broad peak. Okay. So another important thing is that in this region, if there is for primary amines and amides, we can have a peak like this. So this can be for the primary amines and amides. Okay, so this would be the NH bending. You're getting my point? So in this way, if you see, this is an overlay, or if you look into this chart, you will be able to analyze any of the given architectures on FTIR. So you may be asked, suppose distinguish between whether this compound is having an C double bond C bond or not, whether it is an alkyne group or not. If it is an alkyne group, if it is an alkene, if it is having C double bond C, there will be a peak at this region. You just have to draw a line at around 1500 and 300, and you have to see if it is C double bond C, then what will happen? You will be having a peak just after 1500, and you will be also having a sp2ch peak. Okay. Now, if it is an this sp3ch, then you will be having this ch stretching over here just at around 2900. There will be a double peak. Okay. Then again we have discussed about another peak over there. I just forgot. Yeah. This peak was also there. What was that? Yeah, for the CH stretching of the aldehydes, if I tell you find out whether the compound is an aldehyde or not, then you have to look into this additional CH stretching for the aldehydes 2700 and 2800. So in the 2700 to 2800 over here, you have to check there is a double peak or not. This would be here. So this is for the aldehyde CH stage. Okay. So with this, I complete this chapter. If you have any questions, we can discuss. You don't have any question? Okay.
No, sir.